So, so your video is off. So good afternoon, everyone. Welcome to the next session of Special Functions and Number Theory seminar. Today we have Professor James Sellers from University of Minnesota, Duluth, my very good friend. And he'll be talking today on partitions into odd parts with designated summons. Yeah. Over to you. Yeah.
Thank you, Atul. May I share my screen?
Sure. Yeah.
Is everything ready for Gaurav for me to do that?
Yeah.
Okay. Let's see. Okay, and one more. Yes. How does this look, Atul? Is it okay?
Great. Yeah.
Wonderful. All right. Well, then let's begin. Let's begin. First of all, thank you so much for to the organizers for allowing me to give this talk today. It's a great opportunity, and I am very, very grateful for it. I was just speaking with Atul a moment ago, and I am currently in Budapest, Hungary, on a Fulbright semester, and I'm enjoying that tremendously. But I'm also very new to this space, so hopefully the Wi-Fi will be fine and everything. But just thank you for your patience in case something goes awry. And again, thank you for this opportunity. It's wonderful to be able to speak today. I want to highlight my two co-authors on the work that will be discussed today, Shane Chern from the University of Vienna and Xishuo Fu from Chongqing University in China for very fruitful collaborations. So I actually know Shane and Xishuo from their time when we were all at Penn State years ago. And so I'm really, really grateful for the two of them for working with me on this subject. In this talk today, I'm going to spend some time providing historical background regarding this function, which I'll call PDO of n. That is notation that was originally set in 2002 by George Andrews, Richard Lewis, and Jeremy Lovejoy in a paper that I'll talk about in just a moment. PDO counts the number of odd part partitions with designated summands. So P stands for partitions, D stands for designated, and O stands for odd. So this is where the notation comes from, and I'll talk more about it in a moment. And then once we get past that historical background, I'm going to then talk about various new properties for this function. And I'm actually pretty excited about these results. Okay, so let's begin. So again, in 2002, Andrews, Lewis, and Lovejoy introduced these objects, these combinatorial objects called partitions with designated summands. They published this in the journal Acta Arithmetica. And these are built by starting with unrestricted integer partitions and then designating exactly one of each occurrence of a part. So let me show you an example. And I want to spend just a moment on this to make sure that we're clear on what these are and what they are not. So we're going to take the weight 4 partitions, and we're going to build the partitions with designated summands. So here they are. And we're going to designate the parts with a little tick mark or an apostrophe, however you want to view this. Notice that what's happened here is I've taken the partitions of 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. And I am required in each of those partitions to select one of each of the parts, and I must put a mark on that part. So unlike over partitions, where I think some people might see some overlap here, in the case of over partitions, you're allowed to select whether you will or will not put a mark over a part. So in some cases, in over partitions, none of the parts are marked. In the case of these partitions with designated summands, we must select one copy of each part and we must mark it. So for example, at the bottom of the slide, you see the partition 1 + 1 + 1 + 1, and you see it 4 times because we selected either the first part, the first one, the second one, the third one, or the fourth one to mark as our designated summand. So I see 10 items here in this list. And again, I hope it's relatively clear how these differ from over partitions. Not only do you get to select yes or no, whether you're going to mark a part in over partitions. Here you don't get to select, but also in over partitions, we typically, if we mark something, it's only the first instance of that part size, or maybe the last instance of that part size, however you select it. Here, we're allowed to actually mark any one of the copies of the part size. So again, with the 1, 1, 1, 1, we actually could mark the first one, the second one, the third one, or the fourth one. So these are indeed different than over partitions. Clearly, they're related somehow, but they're very, very different in many respects. So in the same in that paper of Andrews, Lewis, and Lovejoy, they denoted the number of these partitions with designated summands of weight in as PDN. And so PD of 4 from the previous example must equal 10. Okay. In that same paper, the authors chose to also focus on a restricted version of this function where all of the parts must be odd. And from there, they denote a new function, PDO of n. And it's that PDO of n that's going to be the thing that we focus on today. So if you go back to the example that I just showed you, and you only look for the partitions where all of the parts are odd, and then you designate one copy of each of those parts, then these are the 5 partitions into odd parts with designated summands of weight 4. So PDO of 4 is equal to 5. So if you go back to that original paper from 2002, you'll see a number of Ramanujan-like congruences that Andrews, Lewis, and Lovejoy proved for both PD and PDO. What I would like to do just for a moment is show you a bit of an abbreviated bibliography of some of the papers that have arisen where the authors have focused on Ramanujan-like congruences for these functions. I do this primarily so that you can see that it's been a topic of interest ever since 2002. So I'm just going to flash some papers in front of you. By the way, I'm happy to share these slides with anyone who wants them. So don't feel like you have to quickly write any of this down. The original paper of Andrews, Lewis, and Lovejoy from Acta Arithmetica 2002. In 2013, Bill Chen and some of his co-author colleagues wrote a follow-up paper in the Journal of Number Theory, again, focusing primarily on PD of n. Nayandip Barua and KK Ojha in the Integers Journal, the online Integers Journal in 2015, then focused on PDO of n. And there are other papers here. You may recognize some of these authors. Paper in Integers in 2016. Let me just point out this top paper on this page. Some authors have realized, rightly so, that there's nothing overly special about PDO in the sense that PDO simply does not allow partitions I'm sorry, parts which are divisible by 2. That's what it means to be odd. And so you can generalize this concept to partitions where parts are not divisible by 3 or k. Of course, you're talking then about k regular partitions at that point. So in the case of this 2016 integers paper, Naika and Girish looked at 3 regular PD partitions. In the same year, Ernest Jha in the Journal of Number Theory looked back again at PD. And then we have additional papers, Journal of Integer Sequences in 2017, looking again at PDO. I had the privilege of writing a paper in 2020 with my Brazilian colleague, Robson da Silva, where we looked now at these K regular PD partitions. Barua again with Kaur, in essence, followed up with that paper with one in integers in 2020 on K regular. And then the last one in this list that I'm going to mention is this paper of Herden and 6 other co-authors. It appeared in Integers in 2023, just about a year and a half ago. And here the authors, they basically go back to PDO and 3 regular and or 3 to the L regular and 2 to the L regular. And it's this paper that I want to focus on for the next several minutes as we think ahead about some of the new results. But I want to point out again, this last paper was just published a year and a half ago, maybe 2 years ago. So in that paper of Herden and his co-authors, they looked at several Ramanujan-like congruences for PDO of n. And at the end of the paper, they shared this conjecture. So I just want to let us stare at this for just a moment. And notice we have 5 congruences here, all modulo 4, and PDO at various arithmetic progressions. Let me make 2 quick comments here, and then I'll go on to the next slide. The one comment I want to make is that these things are actually, some of them are fairly closely related to one another. For example, if you look at the first arithmetic progression, 16n plus 12, and you look at the 4th arithmetic progression in this list, 32n plus 24, you realize fairly quickly that 32n plus 24 is exactly 2 times 16n plus 12. So it looks in particular like the first and the 4th of these might be related somehow. And indeed, that is the case. And so when I get to the next slide, I'm going to walk you through how that is the case. So I just made that comment, so I'll keep moving. It turns out that's a hint of something larger. And indeed, it turns out there's an infinite family of mod 4 congruences in non-nested arithmetic progressions satisfied by this PDO function. And in fact, let's see, when alpha is equal to 2, then you get 16n plus 12. And when alpha is equal to 3, then you get 32n plus 24. And those are indeed the first and the 4th conjectures of Herden. So after I saw this paper of Herden, I decided to look for something larger like this. And indeed, this is what Maple told me would happen, except Maple didn't give me the proof. So I'm going to talk to you about the proof in just a moment. So it turns out that the function PDO also satisfies an infinite family of mod 8 divisibilities, Ramanujan-like congruences. And here it's got a very similar shape. Instead of 4n plus 3 on the inside, here that we had mod 4, we now have 8n plus 7. But one can prove this as well in similar fashion. So discovering and proving these kinds of congruences actually led to 2 papers. I'll just mention them quickly. One of them was a paper in Integers that appeared last year, which was in essence a follow-up to the Herden et al. Paper. And then another one was Shane Chern that we published in Acta Arithmetica, which I'll talk about in a few minutes, where we found an infinite family of internal congruences, and we allow the modulus to grow as an arbitrary power of 2. So I'll talk about that in just a moment. The first paper, the one that I wrote by myself, very elementary proof techniques and so on, very classical techniques. The second paper required much more machinery in modular forms. Okay, so how do you prove these kinds of things? These, say this infinite family mod 4, this infinite family mod 8. Well, one approach is this. You start by proving the first few cases of the congruence family just using classical results, generating function manipulations and dissections. And you prove those, and in essence, prove them almost like they are the basis case of an induction proof. And then if you can find an internal congruence, something like PDO at certain values is congruent to PDO at other values mod 4, this can serve then as the engine for a proof by induction. So since the modulus is not changing in the mod 4 family and in the mod 8 family, this is a perfectly good way to go through the proof. Okay, so did I hear a question? Okay, so let me go ahead and sketch the proof for you quickly. In that paper from 2002 with Andrews, Lewis, and Lovejoy, they proved that the generating function for PDO is equal to this eta quotient, F4 times F6 squared over F1, F3, F12. So I'm not using the usual Q-Pockhammer notation here. I've abbreviated it somewhat into this F sub R notation, which has become a little more common in our literature now. I just want to highlight that the subscript on the F is serving as a common power on the Q's in the infinite product. This is very important. So for example, the F4 actually is a function of Q to the 4 everywhere, and the F12 in the denominator is a function of Q to the 12 everywhere. Okay, so in order to prove, let's say the congruence is mod 4, I need to be able to do 2 dissections on this generating function, mainly because the skip value on the arithmetic progression is a multiple of 2, and it's also a multiple of 4 and so on. So I need to do those, and in order to do that, I'm going to need some lemmas. Now, let me just highlight quickly before we go on, this generating function, the F4, the F6 squared, and the F12 are all ready to be helpful to us with 2 dissection because they're even. The F1 and F3 in the denominator are not so friendly. They're going to require us to do more work on the 2 dissection, but we can handle that. What we need is a lemma that talks about 1 over F1, F3, and I'll show that on the next slide. So one of the lemmas we'll need is a 2 dissection of 1 over F1 to the 4. For those of you not familiar with this, let me just point out what the right-hand side is doing. All of the powers of Q in this first term on the right are going to be even powers of Q. So this is going to give us the even argument terms out of this object on the left once you write it as a power series. And in this other term, all of the subscripts are even, but we're multiplying by 1 extra Q. And so those are going to give us all of the odd powers of Q when I write this as a power series in Q. So this is splitting me up into the even powers and into the odd powers. Let me also point out that this 4 could prove to be very, very helpful later in terms of congruences. Okay. Then we have a very classical result on F1 squared. Again, a 2 dissection. I should point out this first lemma goes back easily to Ramanujan and work that he did with his theta functions. And lastly, we have this lemma on 2 dissections for 1 over F1, F3, as well as F1, F3 in the numerator. And it's this piece right here in this lemma that's going to allow me to do a very easy 2 dissection of the PDO generating function in just a moment. So this is the whole toolbox that I need in order to go through the work that I'm about to show you. Okay, so using these things, I can immediately get the 2 dissection for PDO. And it turns out that the generating function for PDO at 2n is equal to this. And the PDO, the generating function for PDO of 2n plus 1 is this. And I just want to highlight, I don't want to say anything about it yet. I want to highlight that this is equal to this thing squared. I know that's not a very deep mathematical statement. You can see that you could pull out a 2 out of all the exponents, but this is going to come back to us in a moment. That's why I put it in blue. So we'll come back to that in a bit. These actually already appear in Andrews, Lewis, and Lovejoy. So there's nothing new about what I've done here. But you can dissect them again. To dissect them again, and for example, if I wanted to dissect this second term, or this second generating function, almost all of the subscripts are even. The only thing remaining is a 1 over f1 to the 4. But I had a lemma that told me what to do with 1 over f1 to the 4, and so I can do another 2 dissection. And once I do that, I get these 4 generating functions at 4n, 4n plus 1, 4n 2, and 4n plus 3. And it should be pretty clear that the last 2 of these identities are going to give me congruences. The third one is giving me a mod 2 congruence, and the fourth one is giving me a mod 4 congruence, because, except for the 4 out front, everything else here is just a power series with integer coefficients. And when you multiply all those integers by 4, you get multiples of 4. So this object actually is the alpha equals 0 case of my mod 4 family. So I immediately have that case proven thanks to that generating function. So that's cool. Let's keep that in mind. And if you consider these mod 4 for just a minute, then you can actually also prove from this result for PDO of 4n and from this result for PDO of 4n plus 2, you can actually prove these 2 generating function results mod 4. Those will be interesting to me in a moment. However, let me just highlight something quickly. Mod 4, this turns out to be a 2 dissection of this object because all the subscripts here are even. 12 is even, and it's being multiplied by a q to the 1. So this will be the even part. This will be the odd part. So the generating function for PDO of 8n is coming from this, and the generating function of PDO of 8n plus 4, which is 4 times 2n plus 1, is immediately coming from this. So in a moment, I'm going to get some mod 4 congruences just flat out immediately. And next, notice that this object is completely an even function of q. The 2 in the subscript and the 6 in the subscript are even. And so there are no odd powers of q when I expand this as a power series. And that means if I replace this n by a 2n plus 1, then the right-hand side will be 0 mod 4. So I'm actually staring at 3 congruences mod 4 right now, and I think I share them with you on the next slide. So first of all, I get this one. That came from down here, and the right-hand side being an even function of q. And the other 2 give me this. And in particular then, this, because this is an even function of q, will also give me this congruence right here. Now, I want to point something out. See what I did with coloring. Yes. This is the alpha equals 1 case of my mod 4 family. And this object right here was the first of Herndon's conjectures. And it is the alpha equals 2 case of the same family. Notice that if you just multiply this by 2, you get this argument down here. So I'm actually working my way through the first few steps of my proof of this infinite family mod 4 in the process. Very elementary, very elementary proof. Okay, so I just said that a moment ago. And so these results give me the basis case of a proof by induction. And now I need an internal congruence, which will serve as my engine for the induction, and here it is. The theorem is that PDO of 4n is congruent to PDO of n mod 4 for all n. Now, I just want to really quickly pause on this. So I've been doing work in Ramanujan-like congruences for various partition functions for many, many years. I mean, probably 25 or 30 years. And hunting for, identifying and finding divisibility properties for such functions is relatively straightforward. You know, you take the generating function, you expand it several thousand terms. You then ask your favorite computer algebra system just to hunt for arithmetic progressions where everything is divisible by some modulus m, and you get a conjecture, and then you prove that conjecture. But in the case of something like what's on the screen right now, there's a little bit more difficulty. Not a lot, but a little bit, because now you have, in essence, two different functions at play, one on the left and one on the right. And now hunting down what the correct left-hand side and what the correct right-hand side ought to be is not as easy. It's almost like you have one more degree of freedom, and it's just a little bit harder to find. Nevertheless, I found this result and was really pleased with it. And now the proof is very, very straightforward. Let me just walk you through it. It turns out this is immediate because a moment ago, I shared with you a mod 4 result for PDO of 4n, and it turns out that the Herden et al. Paper proved that the same right-hand side mod 4 holds for the generating function for PDO of n. In other words, this was already waiting for me in their paper, and all I really had to go do was confirm that the PDO of 4n satisfied the same right-hand side. And so that immediately gives me a proof of this result. Once I have that, I can now prove my infinite family mod 4 immediately. I've already proven the alpha equals 0 and alpha equal 1 cases. Those were those. I put them in red earlier as well. And now the proof goes through immediately. Here we go. You know that PDO of 4n plus 3 is congruent to 0 mod 4. I've already proven that. And now what you do is you use the fact that PDO of 4n is congruent to PDO of n mod 4. So I come over here and I'm going to replace n by 4n. So I take the 4n plus 3 and I replace it by 4 times 4n plus 3. But then I can replace that by 4 times that again. And then I can do it again just by multiplying by 4 every time. And you can keep doing this. I decided to stop here. And so this gives us our theorem when the alpha exponent is even. Well, how do you handle alpha is odd? Well, you start at PDO of 8n plus 6. We've already shown that that's congruent to 0 mod 4. I'm just going to factor out a quick 2 there just so I can see it. And then I know that PDO of that is congruent to PDO of 4 times that mod 4. So I'm going to multiply by a 4. Then I can multiply by another 4, and I can do it again. But I decided not to to require you to watch me do that too many times. And so that is going to give me the same result where I now have 2 to the alpha times 4n plus 3, but now the alphas are odd. So I have the even alphas. I now have the odd alphas. That's all the alphas. And so I have my proof. And I personally love this because it has a very elementary flavor to it. It would be nice if we could have gotten congruences where the moduli were growing. Nevertheless, it's still a very satisfactory result. So time is short today. I want to share lots of other stuff with you, but I'm just going to point out that you could prove this theorem in the exact same fashion. You find some basis cases, you prove them directly, then you find an internal congruence mod 8, use that as your engine, and go from there. And my paper in integers does exactly that. Okay. So what we did then was I proved these results, and then I proved this internal congruence mod 8. And so it has a similar feel to the one mod 4, but it took a little more work to find it. All right. Now we talk about this work with Shane very, very briefly, and I'm going to be very brief because what I want to say at the end of the talk, I want to make sure I have time for. I've already mentioned these two internal congruences satisfied by PDO. It turns out that the second one is actually part of a larger family, and this is the larger family. And this is a really, really cool set of results. So notice what's happening here is now I have internal congruences. I have PDO at one value congruent to PDO at another. But more importantly, the moduli now are growing as K gets bigger and bigger. And also I want to point out that the arguments here and here are exactly 4 times one another. In other words, this argument is actually 4 times this argument. So as the moduli grow, you have this PDO on one side and a PDO on another, and they're related in that they're congruent to each other mod 2 to the 2k plus 3. That's how is that related to what I was showing you earlier? Well, if you replace n by 2n, you get this. And if you then take the k equals 0 case of that, you get PDO of 16n is congruent to PDO of 4n mod 8. And that's that result at the very bottom of that screen. So what I was doing elementarily in my paper in integers turned out to be a special case, if you will, of a bigger theorem that Shane and I then ended up proving in Acta Arithmetica, and we published that last year. Heavy on the modular forms, and so I won't go into the details of that today at all, but I do want to point out something almost like a work to be done later, and that is this. These results are waiting to serve as the induction engine for some divisibility properties for PDO modulo large powers of 2. Well, what's missing then? What's missing are the basis cases, the initial congruences that one could find. And beyond modulus 8, higher powers of 2 beyond 8, I've actually not been able to find such basis cases. So if someone can find true Ramanujan-like congruences modulo, let's say 16, that are sitting inside of the right arithmetic progressions, then what's on the screen right now would serve as the immediate engine, the induction engine for a proof of an infinite family. It's just that I haven't been able to find the divisibility properties necessary, mod 16, 32, etc., in order to do that. So that would be a really cool thing to take on. I just haven't been able to find those computationally. Okay, I just said that, so I'll keep moving. And now what I want to do is transition in a very significant way. I want to turn a corner, and in the last few minutes that we have together today, I want to talk about this material from a very different perspective. And I'm just going to say kind of an exciting perspective. So for those of you like Atul who know me and have known me a long time, I spend most of my time on divisibility properties, on Ramanujan-like congruences for partition functions. However, I don't spend all of my time on that. And what I want to spend time on now is a different result, which I think is really, really cool and much more combinatorial. So let's talk about that. So I want to go back to something I actually showed you. I think I put it in blue color earlier and I skipped over it very quickly. But the theorem that comes from that is the following, that PDO of 2n for any n is equal to this convolution sum where k runs from 0 to n, and you have PDO of k times PDO of n minus k. So this is the generating function from which one gets the theorem that's higher up on that slide. Namely, that the generating function for PDO of 2n is equal to the square of the generating function for PDO of n. Let me just go to my next slide. Oh. This was the several slides ago, I showed you this identity. This is the generating function we started with, PDO of n. And when I dissect it, I get this, which is equal to this. And I joked a moment ago, well, you could just pull a 2 out. But if you now stare at what's inside these parentheses, what's inside them is exactly this. This is a crazy result. And it leads then to this. So that identity, at least from the world of partitions, in my opinion, is a really, really intriguing, or what I called curious identity. So this identity actually appears implicitly in the original Andrews-Lewis-Lovejoy paper. It also appears implicitly in my integers paper from last year. It's actually explicitly called out in the 2015 integers paper of Nayandip Dika-Barua and his colleague Ojha, where they actually say in their paper, quote, it would be interesting to find a combinatorial proof of this identity. I totally agree. And the way that all the other authors have ever proven this result that's on this screen is to simply do the 2 dissection to get this thing at the bottom. So this is all just generating function manipulation. There is nothing combinatorial about what's going on. So I really appreciate this call, this explicit call from this 2015 paper to try to find a combinatorial proof. So again, this is my reminder to you. And it turns out that the original representation of this PDO generating function is really helpful for congruences, but it is not, in my opinion, really helpful to try to prove this identity in a combinatorial way. So I want to find a different way of thinking about PDO of n, which will allow us to look for more combinatorial things like this identity. So last summer, I was at the conference in honor of George Andrews and Bruce Berndt at Penn State University. And while I was there, I spoke at length with Shishuo Fu, my colleague, about trying to look at this combinatorial identity. Shishuo is an absolute expert at looking for combinatorial proofs of identities like this. And so we decided to start looking for a different approach. And now what I want to do is share with you what we did. So I'm now going to rewind us over 100 years to a paper of Percy McMahon, which appeared in the Proceedings of the London Math Society in 1921. And McMahon looks at these 2 functions. I just want to say as a side note, I believe George Andrews gave a talk in this seminar some months ago. And if I'm not mistaken, this object, A sub k of q, was generalized by George and some of his co-authors, Aldebaran, Tarraso, and George's talk was based on some of that work. So I'm going back now to these same functions. Notice the A sub k of q deals with all possible partitions in the exponent on q in the numerator. And notice that the C sub k of q seems to be looking at odd parts because the exponent on q in the numerator could also be written as 2m1 minus 1 plus 2m2 minus 1 plus 2m3 minus 1 plus dot 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 plus 2mk minus 1. You take the minus k and just split the ones all the way across. And so you see odd parts in the C sub k of q, whereas in the A sub k of q, you don't see that restriction. So if you define something called A sub n and k to be the sum over all partitions of n, which have exactly k parts, m1, m2, up to mk, the A sub n and k are actually summing the products of the frequencies of the parts. So the S1 up to the SK, which are up in here and being multiplied, are actually the number of times that you're having M1, M2, up to MK. You then multiply that, and then you add all that up, okay? If K is 1, then this object above is just the usual sum of divisors function. It's not hard to see that that's what's happening. As you run across all possible partitions, what you're really just running across is all possible divisors of n. So when K is 1, this is just the usual sum of divisors. McMahon's goal was to look at something that would be a generalization. It turns out that you can then show that this sum of the lowercase a sub n and k's multiplied by q to the n, if you sum over all possible n, that basically you get back this a sub k of q. But what is exactly this object doing, the a sub n and k doing when k is fixed? Well, what it's doing is it's calculating all the possible multiplicity combinations, if you will, of all the parts. And if you think about it for just a moment, that's the same as taking a partition, a specific partition with exactly k parts, and counting the number of ways that you can put the little marks, the designations, on each of the parts. You have S1 ways, let's say, to mark the ones, and you have S2 ways to mark one of the twos, and you have S3 ways to mark one of the threes. And if you multiply all those S's together, you're getting the number of different ways to put the marks on the parts in a designated part partition. And so this thing, a sub k, is intimately related to the function PD of n from Andrews, Lewis, and Lovejoy. Well, it turns out then that the same thing is true for the PDO function and this thing C sub k of q that also appeared in McMahon's paper. Remember, C sub k is handling odd parts. PDO is also handling only odd parts. And these lowercase c sub n and k are then counting the number of ways that you can move around the designations. It's a gorgeous result. And so what this means is that this provides us potentially with another way of viewing the generating function for PDO. And this is exactly what I just said, but in generating function terms, this is what we have. So now, instead of looking at the generating function for PDO as this eta quotient where everything is sort of wrapped up together, now what I can do is think of the generating function for PDO based on exactly the number of parts in a given PDO partition. So the focus now is not on the weight in, the focus now is on the number of parts. Fantastic. And as far as I know, no one has seen or thought through using McMahon's A sub k and C sub k in this kind of a connected way with the PD function and the PDO. Okay, so thanks to some work that George Andrews did with Rose in 2013, we can perform certain calculations on the generating functions to make them do what we want, which is fantastic. So we're going to define then a refined version of the PDO function, which simultaneously takes into account the weight in, but it also looks at the number of different part sizes. That would be the K in essence. There's some notation here. I'm going to just work through it, but let me just point out that little l sub d of a partition lambda is denoting the number of different part sizes in the partition lambda. In essence, it's looking at K from my previous slides. And then what Shisho and I have proven is the following. So I won't spend too much time on this identity, but let me just highlight what it's saying. On the left, we're taking partitions that live in PDO that have weight 2n. Remember, The identity is PDO of 2n is equal to a convolution sum on the right-hand side where the total weight is n. So the left-hand side here is a polynomial statement now in x over those partitions, where the exponent is now keeping track of the number of different part sizes. And on the right, we have a convolution sum now. The alphas here have weight k. The betas here have weight n minus k. Remember, that's what the convolution sum looked like. And you have a polynomial identity on the right-hand side as well. So this is, in essence, a one-parameter generalization or refinement, I should say, of the original identity that I showed you a moment ago for PDO of 2n. So this is the generating function way of saying it, where I use the bracket notation to denote coefficient of q to the 2n and coefficient of q to the n. And you see on the left, you have weight 2n. On the right, you have weight n, but everything is being squared. Let me give you an example, because I think an example would help here. Let's take n to be 4, so the weight here is, total weight is just 4. The weight of 2n then is 8. There are exactly 22 PDO partitions of weight 8. They can be broken into two sets. One of them is a set of 8 that have exactly 1 part size, so k would equal 1 in this case. Those come from just 1, 1, 1, 1, 1, 1, 1, 1, and you put the little mark wherever you can, and so there are 8 ways to do that. So those 8 are immediately counted as part of PDO of 8. And then there are 14 PDO partitions of weight 8 that have exactly 2 part sizes. And they come from creating the designated parts for 7 plus 1, 5 plus 3, 5, 1, 1, 1, 3, 3, 1, 1, and 3, 1, 1, 1, 1, 1. Notice those have exactly 2 different part sizes to them. And you can't, if you think about it for a minute, you can't have 3 different part sizes into odd parts here, because that would mean you'd need some 1s, you'd need some 3s, and you'd need some 5s at minimum. And that adds up to 9, and we're only trying to add up to 8. So this is it. These are the 22 partitions counted by PDO of 8. And now what I want to do is, that's sort of the left-hand side of my identity. I've broken them up by the number of part sizes. And now I want to show you how that lands on the right-hand side. If you now take pairs of these PDO partitions, one will have weight k, the other one will have weight 4 minus k. You can break them into two subsets. There are 8 such pairs with only 1 designated part, and an empty set means you have nothing on that side. The vertical line is just telling you where the 2 different partitions are located. Remember, we have a convolution sum on the right. So there are the 8 that correspond to the 8 earlier that had only 1 part size. And then here are the 14 that have exactly 2 designated parts. Now, sometimes there's a designation, 1 on each side of the vertical line. Sometimes both designations are on the same side, as in the case up here and up here. But the ultimate point is these 14 get mapped to the 14 that I showed you a moment ago, and the 8 that I showed you earlier get mapped to the 8. So we have a refinement now of the original identity. And I'm watching my clock here, so let me just close with a few comments. Shisho and I have actually proven a 2-parameter refinement. I just showed you the 1 parameter today. And our proofs basically boil down to Chebyshev polynomial identities. The work of Andrews and Rose that I very quickly highlighted a moment ago pushes us into this Chebyshev polynomial work. The proofs are relatively straightforward. Once you see what you want the identities to be, finding the left-hand and the right-hand side of the identity is not always easy. And I'll just point out that when Shisho and I started this work, what we really wanted was just a purely bijective combinatorial proof of the original identity. That's all we really wanted. And sadly, I must share with you today that we don't have that. So rather than finding just a very simple map between PDO of 2n and the convolution sum on the right-hand side, we didn't find that. But in looking for that, we were able to find the one parameter refinement that I showed you today, as well as a two parameter refinement of that original identity. Shisho and I have submitted our manuscript. It's currently under review, I think, at Discrete Math, and we're hopeful that it will be positively viewed by the referee and that we'll see it published one day. And with that, I will close, and I thank you all very much for attending today.
Thank you, James, for a very interesting talk. Are there any questions? So I have a couple of questions. So one of them is regarding this, the one parameter generalization that you showed. So when you differentiate that identity with respect to X and then put X is equal to 1, you'll be getting identities between number of different part sizes, right? Like,
yes, that sounds right, Atul, although I have to admit, Shisho and I didn't think of that at all. It's a really fun idea, but
yeah.
I didn't think of that.
Okay. Yeah.
So what is your intuition again about what would happen if you differentiate with respect to X and then
say if you differentiate once and then let X is equal to 1, then it is going to add LD of lambda over all these lambdas on one side. On the right-hand side, it is going to be complicated, but I guess when you put X is equal to 1, probably it gives something which is interesting again from a combinatorial perspective.
Very interesting. Okay, I will. I've made a handwritten note, and I will definitely mention that to Shishuo, and we'll see what we can do.
Sure.
Thank you.
Sure. And my first question was regarding the very first slide. So when you had the definition of PD, the partition.
Yes, one moment. Let's see. Yeah. Yes.
So when you had these partitions, 10 different partitions of 4, so this PD function or PDO, they sit, so they are neither compositions because you are not allowing 1 prime plus 2 prime plus 1 also in there. But if you take all of the over partitions and remove all of the partitions from there, like without the overlines, they still won't be the same as these because you say, for example, you have this 4 sets of partitions, 1 plus 1 plus 1 plus 1 with a mark, and which you don't allow in over partitions. So in that way, they are different from the over partitions as well as the compositions. So yeah, that's interesting.
Yeah, they're definitely different in for all the reasons you've mentioned, Atul.
Yeah.
One of the things I find interesting is, over partitions, and I'm sure many of your participants here know, over partitions have received just tons of attention, right?
Yeah.
For some reason, these functions have not. I mean, they've received some. Don't get me wrong. Obviously, I showed probably, I don't know, 10 papers earlier that have had them, but they're all of those papers were about divisibility properties in essence. But you look at the literature on over partitions, and it has exploded, right? I don't know, hundreds of papers, or at least dozens and dozens of papers, and so I'm intrigued and also excited to think that this PDA and PDO functions could be studied more because they are definitely different than the over partitions. Right. Michael, I see that you have your hand up. It's good to see you.
Yes, good to see you. Thank you. So can I really ask the question? Is it fine? Yeah. Sure. So it's a very nice talk. I'm very intrigued about your results, and I was also wondering. It's natural to try to extend this, as you said, like to maybe have mod 3 or higher powers of 3. So what about, you mentioned some paper by, I think, Mahadeva Naika about PD, not O, but not without, but not divisible by 3. Have you studied that? Are there infinite families of congruences maybe there?
So the paper that I mentioned in the list, I had a paper with De Silva from, I think, 2020.
Okay.
where we did what we called K regular partitions with designated sum-ends. So in that case, K regular means none of the parts can be divisible by K. And we were actually able to get lots of results, probably for arbitrary K, if I remember right. So it wasn't like we selected a specific set of values of K. I want to say that we actually did it for an infinite family of values of K. So the answer is, Michael, yes, there's lots of divisibility there. And I will just share with you the reason for that, I think, is because the generating function, even when you go from, say, PDO to PD sub K, the generating function is still an eta quotient. It's still a very nice eta quotient, and it has certain properties that allow one to manipulate that quotient very, very handily. So that has been looked at. Michael, is that what you were suggesting? Is that what
Yes, that's one thing. And then also the curious identity. Is there a class of partitions where the 2 would be replaced by 3, for instance?
This is a gorgeous question, and I have hunted for this for years. I cannot find it. And I will also ask and answer another question, Michael, which is, could it be that, could I even find one other function where, you just change PDO of 2n to f of 2n or f of anything, and then on the right-hand side have the corresponding thing squared? I don't even know of another example of that.
Yeah, James, I just was looking on MathSciNet. So I was actually thinking about the same question, like replacing a PDO of 2n or PDO of n by f of n or f of 2n, and then seeing there are, I mean, I also don't know any of such instances, but Kevin Ford, who is an analytic number theory, but his very first paper was on one-Simon summation formulas. So in Proceedings of AMS. So he has like Q-series identities of this type. One Q-series identity and square of another Q-series identity is where the functions look more and less the same. So you may want to check out that.
I will definitely do so. Yeah. So Michael, I don't know if I answered all of your questions. I'm saddened to say I couldn't answer any of them in a positive way.
Well, I believe you will come to Vienna soon. Is that correct?
That is correct. Yes.
Then we can continue our discussions there also. Yeah, I'll be happy to talk with you in Vienna.
That would be wonderful. Thanks. So yes, it's wonderful to be here. I'm only about 3 hours train ride away from you right now. So that's fantastic.
Okay.